the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And in this video, I will review how to determine the domain of a given function. So let's get started. In mathematics, when we talk about functions, our emphasis is split between two things: evaluation of the function and domain restrictions. Understanding domain restrictions on functions and how to arrive at the true domain of a function is so important in mathematics and the sciences that your professor is likely to ask you a domain question on the majority of your exams, if not all of them. In general, linear and polynomial functions, sinusoidal functions, and exponential functions do not have restricted domains. That is, the domains of these functions are the real number system. Before any math lawyers raise their hands and state, "You didn't mention functions like x to the 2/3 power," it's true. There are a lot of other functions with the real number system as their domain, but I'm just listing a few function types as examples. As for functions that we have to watch out for when it comes to domain, these come in two types: functions with explicitly restricted domains and functions with implicitly restricted domains. Let's take a look at the first group. Functions with explicitly restricted domains are, well, just that. You're given a function, and alongside that function is a clearly stated domain restriction. It's uncommon in math textbooks to see a function like this, having an explicitly restricted domain. Honestly, I'm not sure why authors have chosen to forego these examples because, despite their lack of appearance in textbooks, they are very common in real-world applications. Albeit, people often do not write down the domain restrictions, rather, it's left for the reader to figure out. For example, the number of Facebook users since 2004 can be represented by the following function. This is an exponential function and naturally does not have a domain restriction. However, once we insert the context of this problem, we should really apply the following explicit domain restriction. This is because Facebook did not exist prior to 2004. Most real-world applications have these explicit domain restrictions. Just like in the previous example, you may have to infer the restriction because the person who developed the mathematical model didn't clearly state the domain restriction. Another common type of function with an explicitly restricted domain is a piecewise-defined function. This function takes on one behavior if x is between -3 and 0, and a completely different behavior if the argument is greater than or equal to 0. The domain has explicitly been restricted to the interval -3 to infinity. I hope that sheds some light on explicitly restricted domains. Now let's take a look at implicitly restricted domains. If a function has an implicitly restricted domain, that means that the function type has an issue at certain input values. For example, f of x is equal to 1 over x minus 2. The person who gave you this function did not explicitly state any restrictions for the domain. However, the function type itself implies a restriction. X cannot be 2. The function types that imply domain restrictions are rational functions, many radical functions, non-sinusoidal trigonometric functions, and logarithmic functions. This list is not exhaustive, but covers most common examples. The rest of this video will focus on functions with implicitly restricted domains. In this example, we're going to take a look at the domain of a composition of two rational functions. There are a couple prerequisite skills that you need here, actually quite a few. First of all, you have to know what a rational function is. You also need to know what a composition of functions is. So to determine a domain of this composition, first thing we're going to do is note that the function that we're inserting into f, which is g of x, is equal to 1 over x plus 2. And that itself has a domain issue. So right at the get-go, We're following the order of operations just like you would with any composition. That internal function or innermost function, you have to worry about the domain of that one first. So we know that in that case, x cannot equal a -2. So we'll make a note of that. And then we will go ahead and insert g of x into f of x. We end up with a compound fraction, which we clear using the LCD of the minor fractions within that. Do some distribution, do some arithmetic, and we end up with this expression in the end, 3x plus 5 over -2x minus 3. This also creates a domain issue, so we know that that denominator cannot be 0, so x cannot be a -3/2. So we have these two domain restrictions. From this point, we would go ahead and do what we're used to doing, which is draw out a number line, just mark out on that number line where our domain cannot exist, and that will tell us, through some highlighting here, what our domain actually is, and we use interval notation for that. So as a quick summary, when you're dealing with rational functions, you really want to make sure their denominators are non-zero, and when you're dealing with compositions of functions, you deal with that innermost function first, make sure that its domain issues are noted, do the work to clean up the composition, and look for any domain issues at the very end as well. You should also make sure that you note as you do your work in between the cleanup if there are any other issues that come up. If we had another division by 0 that comes up in there somewhere, you should make little notes on the sides. Let's turn our attention to even-indexed radical functions. And by even-indexed, I mean square roots, fourth roots, sixths, eighths. These all kind of function the same way. You just want the radicand, the interior of the radical, to be non-negative, greater than or equal to 0. So if you take a look at this function here, we're just saying 6t squared plus 5t plus 1 has to be greater than or equal to 0. At that point, depending upon what is the structure of the radicand, you'll use some type of method or technique to solve that inequality. In this case, this is a quadratic inequality, and so I use my own little technique here to solve this quadratic inequality. You could use whatever you were taught way back in your algebra course in high school or algebra 2 in college. But no matter how you do it, in the end, you get down to this domain. Remember, because the radicand is allowed to be 0, you will include those endpoints at -1/2 and -1/3. To summarize, all even-indexed radical functions require that the radicands be greater than or equal to 0. So you'll use some type of method to solve those related inequalities. Once you've done the work to find the domain of a radical function with an even index, you'll find that finding the domain for a logarithmic function is very similar. The only difference really is that the argument of a logarithm must be strictly positive. It cannot be 0. So we kind of go through the same work. And if you take a look at this function, the actual argument is very, very similar to the one we used in the radical example. Instead of t's, we have n's, but it's 6n squared plus 5n plus 1. We just want that to be greater than 0. And therefore, we get the same type of domain. We cannot include the endpoints there because we cannot include when that quadratic inequality becomes 0. So -1/2 and -1/3 are not included. But otherwise, it's similar. So as a quick summary, when working with logarithms, you just want the argument to be strictly positive. Again, just like the radical example, you're going to end up having to use some type of inequality solution style, whether it's, in this case, quadratic inequality, or it could be a polynomial inequality, or any other type of inequality. We now arrive at the granddaddy of all the examples in this video, and this is really what we would call an arithmetic combination of compositions of functions. That natural log of -1 over e to the v minus 4, that's a composition of two different functions, a rational function and a logarithmic function. And then that plus sign is an arithmetic sign, right? So you're adding two different types of functions. And finally, we have a radical function that is composed with a quadratic function. So there's a lot of stuff going on here. What you need to remember is the order of operations. Work from the innermost parenthesis outward. So I'm going to focus for a moment on that -1 over e to the v minus 4. Specifically, I'm going to mention that e to the v minus 4 can't be 0, which gives us our first domain restriction, that v itself cannot be a natural log of 4. Then I grow out of that, and I mention the fact that the argument of a natural log must be positive. So in other words, -1 over that e to the v minus 4 must be positive, which therefore implies that e to the v minus 4 must be negative, right? Because a negative over a negative is going to be positive. And that gives us our second constraint, that v itself must be less than the natural log of 4. And finally, moving over to the second term in this summation, we have the square root of that quadratic function. And again, because it's an even radical, we know that the argument must be greater than or equal to 0. I just multiply both sides by negative, and I use my quadratic inequality solution style to arrive at the fact that v must be between 1 and 2 inclusive. Now that we have 3 different conditions ready to go, v cannot be a natural log of 4, v must be less than the natural log of 4, and then v must be between 1 and 2, we just draw out a number line, highlight the regions of possible solutions. In other words, we put an open circle around the natural log of 4 because we can't have that. I shade everything less than the natural log of 4 because we want that to be true. And I shade everything between 1 and 2. And then you take the intersection of everything. And the intersection of everything starts at 1 and goes all the way up to natural log of 4, but does not include the natural log of 4. That is the domain of our function. So in summary, when given a composition of functions or an arithmetic combination of functions like we have here, what you're going to do is use the order of operations, work from the inside out, determining the domain restrictions as you move forward, or in some cases, determining valid domains as you move forward. But in the end, you take the intersections of all the valid domains, and that will be the domain of your arithmetic combination of compositions of functions. On days where you have clouds or a mixture of clouds in the sky, as the sun shines from above, the clouds will block that light. Not all of it, obviously, if it's not completely overcast, but wherever you have a cloud in the sky, you have a shadow on the ground. And this is very close to how I think about finding the domain of a function given its graph. The idea is that you have light shining above, and wherever the graph exists, it casts a shadow down to the horizontal axis. But you have to also worry about light shining from below and casting a shadow up to the horizontal axis. Here's the graph of a function. And by the way, that vertical dotted line is a vertical asymptote. The function doesn't exist there. So starting from the left-hand side of the graph, if you can imagine a light shining from above, there'll be a shadow cast from -infinity all the way up to, looks like -1.6. So you'd have that shadow, and so I'd highlight or shadow the horizontal axis. But also you have light shining from below, so from -1.6 all the way up to -1, you have that shadow from below, also creating this little highlight on the horizontal axis or shadow on the horizontal axis. At -1 itself, we don't have a function to cast a shadow from above or below, so there's an open circle there. From -1 all the way up to +1, you can see if you have a light shining from above, it will cast a shadow onto the horizontal axis. However, at 1 itself, light shining from above or below will not cast a shadow onto the axis, so I'll create a little hole on the horizontal axis right there. And then from 1 until 2, technically, actually let's go just from 1 to infinity, and I'll explain why 2 has a shadow cast onto it as well. But from 1 all the way to infinity, if you shine a light from above, there'll be a shadow all the way down onto the horizontal axis. Now, there is a little trickiness here, right? Because at x equals 2, I'm assuming the horizontal axis is the x-axis. At x equals 2, I'm saying there's a shadow cast there. That's because at a height of 4, that graph is solid, so light from above will hit that solid dot and create a shadow at x equals 2. So this is the easiest way, in my opinion, to determine the domain of a function given the graph of a function. We can see from this the domain is negative infinity all the way to -1, union -1 to +1, union 1 to infinity, and all of those edges are not included. Thank you for watching this video on determining the domain of a given function. As always, this content should be prerequisite to the course in which you're currently enrolled. If you found this material unfamiliar or if it was confusing to you, then I recommend you click on the provided relevant prerequisite links listed below for further help. However, if you find you're continually doing this, you might want to consider speaking to your instructor about other course options. On that note, I sincerely hope these videos help you achieve success in your transfer level math and science courses. Cue the music.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.